Everybody, welcome to this Icon seminar, and happy Halloween. My name is Keith McGrath. I'm assistant professor in the aeronautics and astronautics school here at Purdue. And it's my distinct pleasure today to introduce today's seminar speaker, Professor Jackson Kulik. Professor Kulik received his bachelor's degree in mathematics at Texas Tech. And then his PhD in applied mathematics at Cornell University. Currently, he's an assistant professor in the Department of Mechanical and Aerospace Engineering at Utah State University. Let's welcome our speaker.
Thank you very much, Keith, Dr. Legrand. It's been a pleasure being out here at Purdue. It's amazing to be on such a vibrant and large campus. It's just really cool you all get to be here and learn from all the people I've met today. Today I'm going to be speaking about multilinear algebra, numerical multilinear algebra, as it applies to dynamics, control, and estimation. A lot of the work that I do is in the space domain, but a lot of these methods are applicable in any domain, really. To talk a little bit about the setting for what I do, and sorry, let's get rid of that. One of the big cases I look at is some of the challenges we encounter with satellite dynamics in cislunar space. There we sometimes have limited amounts of time where we can observe objects. We have high nonlinearity of dynamical systems and chaos. We also have limited information and the need for autonomy due to time delays for communication just from the distances involved, and also because there are lapses in communication as satellites pass on the other side of the moon, for instance. All these things kind of bring us to a point where we want autonomous solutions for doing GNC of highly nonlinear dynamical systems with small amounts of information. With that, the talk's going to go a little like this. First, I'm going to begin as a mathematician with the background math. And so bear with me for a little bit talking about the state transition tensor methodology. Then we're going to talk a little bit about some of my graduate work and how we can use tensor eigenvalues to solve problems that tell us about how linearizations that we find in all of our controls and estimation, basic work, how we can calculate and quantify errors with respect to those. Finally, I'm going to talk about some recent work I've done using the canonical polyadic decomposition for uncertainty propagation in dynamical systems. So with that, the system that we know and love is we begin with some nonlinear dynamical system whose vector field is defined by this vector field F, our dynamics. What you might be more or less familiar with, depending on the context you're in, is the flow map. The flow map is just the operator that is the solution of our dynamical system. It gives the flow for over some time t that satisfies the dynamics given by this vector field F. Okay. Now, a lot of the times when we consider doing control, it involves linearizing or taking Taylor series expansions around some reference trajectory. In the most general case of this, what we're looking at is the Taylor series expansion of this flow map operator here about some reference trajectory. And if we do that, what we can see is how initial perturbations to our trajectory evolve into some perturbations from our trajectory at the final time. Here we have these state transition tensors, they're called, which are just the partial derivatives of the flow map with respect to the initial states, assuming the flow map for some particular time of flight and some particular initial reference solution here. Okay. Now, it might be a little unclear at this point what I mean when I write this notation of this nth order partial derivative and then multiplied with this vector raised to the nth power. I'm going to explain that in more detail coming up, but really this is kind of a contraction of a tensor with some vector or multiple copies of this vector. Okay. Now, I want to motivate this with a problem of interest. Sort of before we walk with controls, let's just crawl with dynamics. One of the most simple things we can do when we're talking about linearization is about linearization of the dynamics themselves. So consider that we might have some reference trajectory here in black about which we're linearizing. And then we can consider how a perturbation from that reference trajectory evolves over time. Say we start out with some spacecraft on a trajectory. It starts at the reference point, the same position, but has some offset initial velocity, this delta V naught. If we use a linear approximation, we might take this dotted line trajectory. But under the full nonlinear dynamics, we might take this other trajectory here in the dashed line. What we might be interested then is how different are these dynamics, the linear approximation versus the nonlinear. Now, if we look at that problem and we Taylor series expand, we can say that the final relative position from our reference trajectory is going to be approximately given by this linearization, the sensitivity of the final position to the initial velocity, matrix multiplied with that initial velocity perturbation. And then we have these higher order terms here, where this is given by some contraction of this third order tensor with two copies of this vector here. And then some even higher order terms in that initial velocity. Looking at this tensor here, we could say and pose a certain question. Given that we have some limit on our initial perturbation size, say we're considering for systems engineering purposes that our initial velocity from this reference trajectory is never going to be bigger than some big R here. We're in some ball of radius R. How big can the error in our linear model be for the worst case subject to that constraint? That would be posed as this optimization problem here, where we're looking at delta V's within this ball, and we're looking at the size, the 2 norm of this third order tensor contracted with our initial velocity. Now, this is going to be one of our motivating problems, and I'm going to get in a second to how we can go about solving this constrained optimization. But I'd like to show you that we can solve more interesting problems as well. To frame this, something that happens a lot in rendezvous and proximity operations planning is using the Hill-Cloesi-Wiltshire equations or some other state transition matrix to solve for your controls, just a simple impulse to get you from one point to another one that you want to get to. Say this delta RF star is the final offset you want to achieve from your original reference trajectory. And you're trying to calculate some initial velocity impulse that's going to get you there. If you use some linearized model like the HCW equations, it's just a simple matrix inverse to calculate some control delta V naught sup 1 to get you there. If you implement that in practice, though, you're not going to get exactly where you want under the full nonlinear dynamics. You might be interested in, maybe your satellite doesn't have the bandwidth computationally to really solve this problem above the linear approximation. What sort of issues are you going to run into under those situations? How far off are you going to be? Here I'm just, showing you that little matrix equation that we have that says our initial velocity, if we use this linear model, is going to be given by some upper right block of this state transition matrix, the sensitivity of the final position to the initial velocity, inverse times the final position offset we want to achieve minus how our initial offset is going to propagate. This is sort of our linear understanding of what's going to happen and how we should solve for our impulsive guidance. Now what we can do is we can take that solution, we call it delta V naught sup 1. It's our linearized guidance solution. What we can do is take our Taylor series model that we had before for the dynamics, and we can substitute in this delta V naught sup 1 right in here and contract it. Now, if we had a certain final position, we could, of course, evaluate this first by taking this matrix inverse, multiplying that, and then doing the contraction with our tensor. On the other hand, what we might do is form the full tensor that comes from contracting this tensor with this matrix here first instead. That's going to give rise to this other tensor here that I'll call the guidance error tensor. And so just like before, we can talk about the errors that are possible here in our misdistance and what the maximal misdistance is given the size of the transfer we want to achieve. How far off are we trying to go? Okay, if we can solve this optimization problem that involves this tensor here, where I'm writing this out in Einstein notation, kind of the output indices of this matrix contracting with the covariant indices of this partial derivative tensor. If we form this tensor, all we have to do is solve this constrained optimization problem. Now, we can simplify it a little bit further. And instead of considering our optimization over some ball of a certain size, what we're looking at is a homogeneous polynomial. And the homogeneity property just tells us that we can shift this to being an optimization over the unit ball instead. So as long as we can solve any constrained optimization of this form over a unit ball, we can solve it over any arbitrary one as well. And this is sort of a technique that was first raised with Dan Shears and Erica Jensen's group looking at tensor eigenvalues. It's been in the literature for numerical multilinear algebra how to solve these problems for about a decade now. And I want to show a little bit of the analogs here that we have to regular numerical linear algebra techniques. So you may or may not be familiar with the concept of an induced matrix norm. The idea behind these is it's a constrained optimization problem like we were just looking, where we are looking at the action of some matrix on some set and trying to look at how big that set gets stretched out. In this case, we have the unit ball, we take all the vectors on the unit ball, we run them through our matrix, and then we look at the ellipsoid that we get as a result. And what we're interested in is how far does that ellipsoid get stretched from the origin. Basically, we want to look at the maximum singular value of that matrix, and that tells us about the geometry of this ellipsoid. Now, the singular values can also be defined in terms of the square root of the eigenvalues of the sort of square of the matrix. So we have this matrix A, but if we take A transpose A, that is going to be sort of related to the squared outputs of vectors that we run through our matrix. Okay, and that's why singular values are related to eigenvalues of this matrix. This is going to show up again later with the generalization to tensors. So while we don't have this nice analytical geometry where a linear operator maps a sphere into an ellipsoid, a tensor, viewed as a homogeneous polynomial in multiple dimensions, does not map a sphere into any sort of nice shape. Maybe there are some algebraic geometers in the audience who understand what the sort of objects we get out of this are. But at the end of the day, it doesn't necessarily matter for our question. Our question is instead, what's the farthest this shape gets from the origin? How big is our unit sphere getting stretched? Okay. And so we're interested in defining these tensor-induced norms, where we're saying I run by contracting some vectors with my tensor and looking at the 2 norm of the output, how big can that 2 norm get? And that's giving me an idea of how big is my tensor by looking at how it acts on things. That's where we call something an induced norm, okay? And you'll see this corresponds to the problems of interest that we had before. Those are induced norms of those two tensors, B propagation and B guidance, those error tensors. So if we want to go about finding these constrained maximum, first let's define another tensor here. So using Einstein notation and the Euclidean metric tensor, so this is just the identity matrix, very fancy. So it's 1 if alpha is equal to beta, and it's 0 if alpha is not equal to beta. I could have just written identity matrix here. Then if we take the output of our B tensor and our output of our other B tensor and contract them with each other through this Euclidean metric tensor, then we get this square tensor. This is essentially the same thing as when we took A transpose A. We're basically taking the output of A and the output of another copy of A and contracting them with each other. Okay. And the nice thing about this tensor is that when we contract it with 2m copies, if B is originally in 1m tensor, meaning it has one output index, one contravariant index, and m covariant indices or input indices, kind of those lower partial derivative terms, then what we're going to get is that this B tilde is a 2m order tensor, and it's purely covariant. That means it just takes in these inputs and produces a scalar if you contract them all. Okay. And the nice thing is when we do that, it's the same thing as contracting our original tensor with m copies of the vector, then taking the 2 norm and squaring it. Okay. So this is really related to our induced norm. Okay. So we can then calculate the a generalization of our eigenvalues. And these are going to come about from applying the method of Lagrange multipliers to that constrained optimization problem we have. If we do that, what we're going to get is the following equation called a Z eigenvalue. With tensors, there are actually multiple different types of eigenvalue generalizations. There's Z eigenvalues, H eigenvalues. There's a number of different letters you can put before the word eigenvalue, and they correspond to different standards and generalizations of your eigenvalues and eigenvectors. Z eigenvalues arise from taking our constrained optimization and applying method of Lagrange multipliers. And in it, you'll see that we have a unit norm constraint here. So what it is we contract B tilde with 2m minus 1 copies of the vector, and that's going to leave a single vector at the end. And what we're doing then is looking for that vector that's outputted and left behind to be in the same direction as the vector that we're starting with. Finally, we need this extra condition that it's on the unit ball, because otherwise this scale factor lambda by which you grow would be different if you look at different shells, essentially. If I'm looking at something that's radius 2 instead of radius 1, my eigenvalue for the set of radius 2 is going to be 4 times as big as my eigenvalue at a lower order. The thing about matrices is it doesn't matter which size ball you look at, it's still going to be the same. We don't have that luxury here. Okay. And finally, we get that the maximum eigenvalue in this sense is going to be equal to the maximum value of this term here. Now, there are numerical methods to compute this that are actually very nice theoretically, or as nice as you really get in the numerical multilinear algebra world. Everything is much more pathological than it is with matrices. But this is one algorithm that has guaranteed convergent properties. It's not necessarily guaranteed to converge to the largest eigenvalue eigenvector pair, but it will always converge to a eigenvalue eigenvector pair, and it tends to converge to the largest. Okay. The radius of convergence of this algorithm for different eigenpairs is not completely understood, but it really is the radius of convergence will be larger the larger the eigenvalue is. And so this is called symmetric higher order power iteration. And it's a generalization of the power method for finding the largest eigenpair of a matrix. Okay. And if you've ever seen the matrix power method, all it is you take a vector, multiply it with your matrix, get the output, do it again, do it again. As you do that, more and more you get dominated by the largest eigenvector direction. Okay. And you throw in a normalization in there to keep it stable and make it work. So we essentially do the same thing with our tensor, but here to get a vector out, we have to just contract away 2m minus 1 times with this 2m ordered tensor. Okay. Then it follows that if we take this procedure and maybe start at a number of different points to make sure we find the largest one, then the 2 norm of the tensor will be given by the square root of the largest eigenvalue of this squared tensor. It's exactly like what we had here. Isn't that kind of nice? So we can apply this back to our propagation problem of finding the largest divergence between our nonlinear model and our linear model of our dynamics. And if we do that, you'll see that I look for a Leo orbit that's ISS-like and the gateway NRHO at how well the linear dynamics perform, essentially. And this tensor norm is going to tell us, essentially, for a given size of the ball, our initial velocity ball, how accurate is our linearization going to be with that? Okay. And so here it's in units of seconds squared per meter. And so if I multiply this by meters per second for my velocity, you'll see that I'm going to get, let's see. Is that right? Well, turns out my thesis work has a unit problem in it. Oops. No one caught that at the time. Sorry about that. That's really embarrassing. But looking at the trends of these, what we see is that with the ISS-like orbit, we actually only get linear growth in time of this tensor norm of our second order state transition tensor. And what that tells us is that essentially the performance degradation you get in using a linear model is going to essentially be linear in time. Okay, that tells us that two-body dynamics are really tame, essentially. With the NRHO, we'll see that we get much, much higher values here, and that they peak around the paraloon passage time. So if we start at apolloon and go to paraloon, that is going to be a very, very sensitive time to our initial velocity. And our linear model is going to be horrible at capturing what's happening there. And a lot of that comes from, if you ever see those space bananas that we get around paraloon, those have some curvature to them that can't be captured by a linear model. Looking at our transfer misdistance problem, we actually see that things are more tame in some sense for the Cislunar problem. So if we're looking at quantifying and using linear guidance and figuring out what our misdistance will be if we implement that linear guidance, it actually isn't a bad thing to be in a very nonlinear, very chaotic, sensitive system. In some ways, that's going to constrain what our velocity looks like at the beginning. It's going to make it much smaller because you're very sensitive to it to get to someplace. And as a result, we're still going to have these peaks where these correspond to what I call relative transfer singularities. These are times when your state transition matrix, the upper right block of it becomes singular. These correspond to pinch points in the debris problem, and also the bifurcations in the number of solutions to the multi-revolution Lambert problem. All of these phenomena are related to each other and correspond to these peaks here. They're essentially when the in B guidance, you'll recall there was an inverse of a certain matrix. And that matrix is not invertible at certain times. It's that upper right block of the state transition matrix in orbital mechanics problems. And so a little lesson here is that linearized guidance actually might not be that bad of an idea as you might think it would be in some of these more nonlinear dynamical systems. Even though you have a worse understanding of where something is going to be, if you use this model for planning maneuvers, it actually isn't as bad of an idea as you might think it would be. The more complex problem actually is simpler in some respects. Okay. Now, there's a couple other applications we can have for these tensor eigenvalue methods. The first of these is to look at nonlinearity indices. So some of you might be familiar with this work from John Junkins and others that's been around for maybe 20 or 30 years now. And the idea behind this was to quantify the nonlinearity of a dynamical system in some particular coordinate set. And what they did is they looked at how does your linearization change as you change your reference point, okay? So your linearization here is your state transition matrix. And we can look at how our state transition matrix changes as we are looking at a different point, perturbing it by this delta x knob for our reference point. And we might then normalize by how big our state transition matrix is in general. So John Junkins' idea that's gotten used all over the place to quantify, is this a good coordinate set for my dynamics, is to look at this and to sample over lots of different perturbations, and then just take the largest of these. Now you might be primed to say, we've got something that looks like an optimization having to do with some matrices here that are varying. And some of you in the room might realize that if we look at a state transition matrix and we change the reference orbit, how that state transition matrix is going to change is going to be according to the next highest order derivative. It's going to be according to that second order state transition tensor. So if we modify Junkins's index a little bit to make it scale free, that is, we divide by the size of our perturbation that we're looking at, then we take the limit as that perturbation goes to 0. We get the definition of a derivative here. Yeah.
I'm sorry, what is the notation for this A and B, the norm?
Yes. This is to make it more general in the sense of these, you might just think of these as being like the 2 norm in general, but this represents the norm that the constraint is on and the norm of the output. Does that make sense? So the upper norm is representing for me right now the output norm, and then the lower index is representing this input norm. Thank you. Now, with that, we see that we get the definition of our derivative here. We're looking at some function evaluated at some slight perturbation away minus the function at the reference point, and then dividing by our distance that we're going by, this delta x. As we take the limit of that going to 0, we get a derivative. And that is going to give us our second order state transition tensor, this psi term here, which is our second order partial derivative tensor. In the top, some induced norm of it, in the sense that we've discussed already, divided now by an induced norm of our state transition matrix with the same norms. What we can look at is the one that is most similar to John Junkins' original one is if we take the induced Frobenius 2 norm. So we look at the Frobenius norm of the output. So not contracting it all the way to get a vector, but only contracting our tensor once to get a matrix. And then looking at our constraint being the unit ball in regular space, okay, our 2 norm. If we do that, we have essentially this exact definition up here. with this enrollment. Now, I haven't talked about how we compute the Frobenius norm, the induced Frobenius norm of a tensor. What that looks like defined here is exactly what I said, this Frobenius norm of the output, and our constraint is on the 2 norm of the input. We can get at this in actually a really simple way, even simpler than dealing with our tensor eigenvalues. If we flatten out our tensor along a certain axis, that is in this particular fashion here, then the desired norm is given by the induced 2 norm of this matrix, which is just the largest singular value of that matrix. So we've got this, let's see, tall, skinny matrix who we have to take its induced 2 norm of, and that's the largest singular value of this matrix. And so it turns out computing the kind of scale-free version of John Jungus's original index can be accomplished if you have the second order partial derivative tensor, the state transition tensor, and you flatten it and take a singular value, which can make it one of the big problems with existing work that utilizes these indices is, one, are you sampling enough? In the original formulation, you're taking a bunch of random points on some ball and then saying, let me compute the STMs along this, and then seeing how different they are. Did you compute enough of them? And how big was your ball? And if you're doing this to compare coordinate sizes, a lot of the times, in different coordinates, you might be looking at a different size ball. And are you really being fair with the size of ball that you're choosing? In this way, you can avoid all of that. And there's a number of other nonlinearity indices that we can look at. Erica Jensen had a set of them. I've got a set called Demon that I think is really nice that looks at the something very similar to her Tiemann. But I think that this one is a really good, easy one to use that fits the original spirit of the nonlinearity index. I'd also like to plug a little work that I've done with Dr. Legrand here. What we can do is we can also apply this problem to uncertainty propagation as well. So here we have an uncertainty-informed nonlinearity index that we use in the context of Gaussian mixture splitting. And the idea behind this index here is that if we have some partial derivative tensor here, denoted more generally for some function g, and we have g2 being its second order partial derivative tensor, we can look at the norm induced by some covariance matrix, the initial covariance here, and that can be our original constraint. We want to look at some initial uncertainty set and say the 1 sigma set of that. We then want to look, as we propagate through this nonlinear function, things that start on that uncertainty set, how big can the linearization errors get from things on that set? And we could stop there and look at that exact question of how big they are, but we might say, how big in what sense? One thing we can do is we can look at, if we take the covariance, our initial covariance, propagate it forward with our linearized function to then get another Gaussian distribution with some covariance, or maybe not even assuming Gaussianity here. We get this other covariance, and we use that now as our metric to assess how big these errors are in this uncertainty weighted sense at the end. And so that will tell you on the scale of your distribution, are they large or small? Whereas if you didn't do that normalization at the end, it would just tell you how big is this in physical units. One might be useful, one other might be useful in some of those instances. We sort of just have this diagrammatically here where we look at linearization error, and then we're whitening essentially and looking at how big that whitened linearization error is. Now, finally, I'll talk about another set of work that I've been doing recently that doesn't involve tensor eigenvalues, but uses another formalism for it. This is the canonical polyadic decomposition. And I know that there's some work here at Purdue that Kathy Howell and Professor Dye have done with the Koopman operator and canonical polyadic decomposition. So seems to be an idea that's kind of really on the minds of a lot of people right now. And I hope this will give you something. So the problem that interested me to begin with here is one about moment propagation. So assume that we begin with some Gaussian distribution, and we know it's moments. Okay, we have a mean and a covariance. And we want to use the state transition matrix and the second order state transition tensor, these partial derivative tensors of some nonlinear function, in order to get approximations of the moments of our distribution as we pass our Gaussian distribution through some nonlinear transformation. What are those final moments? What do they look like? What's the mean and covariance? Now, this is a problem that's been solved and used since the early 2000s for nonlinear uncertainty propagation. And the idea is that if we have access to the initial moments, including the fourth order initial moment tensor, which you can get from the second order covariance matrices in the case of a Gaussian, then all it comes down to is calculating these three different terms. This is your linear contribution that comes from your state transition matrix and how a covariance maps with that. Then we have this term that is somewhat related to the propagation of the mean. And finally, this other term here that is more complicated involves this kurtosis tensor, the fourth order moment tensor. And now what you'll see with these is that these two are easy to compute. We can kind of come up with the computational complexity of each of these calculations by looking at the number of indices. It's basically the number of for loops you would have to go over to calculate one of these things. Even if the indices are there at the end, that's telling us kind of how many indices we have to look through when storing our final elements. How many times we have to do that calculation over and over. And then these K and M indices that are repeated indices that are getting contracted away, they're summed over. Those are the number of for loops that we need to actually do the computations, to do the multiplications and additions that come together when doing these contractions. Okay, so here this is a fourth order computation. You can get it down smaller if you do it one step at a time. This is also a cheap computation, but this one is not here. You'll see that it's also very coupled together. This fourth order tensor is going to be contracted with these two tensors, and we count 6 indices. So if this is like a 6-dimensional vector we're considering, state space, like position and velocity space, this is going to be an n to the 6th, where n is 6, number of operations sort of deal. And if we go further than this and look at higher order approximations and higher order moments that we try to approximate, it only gets worse from here. We have things that's computational complexity is above order 6. Okay, it's kind of bad. Now, the methodology we're going to use is the canonical polyadic decomposition of a symmetric tensor. This is sort of the generalization of the eigenvalue decomposition or the singular value decomposition, or one of them. It's the sort of low rank decomposition for tensors. And the idea here is that a rank 1 tensor, okay, to begin with, a rank 1 matrix is a matrix you get by taking an outer product of 2 vectors. It's a matrix that only has 1 vector's worth of information, essentially. Okay, that's a rank 1 matrix. Now, a rank 1 tensor is something that has 1 vector's worth of information for the whole tensor strand. So what we have here is if we define this sort of tensor product term here, raising it to the nth power, that's saying we're going to take the same vector and then take outer product of it with itself, m different times. And that's our simplest sort of unit that we can have. It's a rank 1 tensor. Now, the canonical polyadic decomposition is saying, let's write our tensor as a sum of a bunch of rank 1 tensors. Okay, and we don't know ahead of time what this rank is going to be, how many of these we need. With matrices, you only ever need as many as the dimension of the matrix. If I have an n by n matrix, I need n factors. With a tensor, even if it's an n by n by n by n tensor, you might need r bigger than n number of terms to get it. And there's no way of knowing really ahead of time what those are going to be. The next little piece of machinery we'll need is whitening transformations. So the idea behind a whitening transformation is that it takes an arbitrary Gaussian or an arbitrary covariance that corresponds to some ellipsoidal region, and it casts it to a standard Gaussian whose regions of kind of constant PDF value are spheres instead. So it takes ellipses to spheres, and it takes arbitrary Gaussians to the standard Gaussian, whose covariance is the identity matrix. And there's many whitening transformations that you can come up with. They're all related to matrix square roots of your covariance. Okay. That can be, for instance, the Cholesky factors. Now, what we can do is we can note this other fact here that if we have a standard Gaussian distribution and we look at its higher order moment tensors, one fact you'll probably be aware of already is that a Gaussian's moments are all determined by its first two moments, its mean and covariance. And in particular, the fourth order moments of a standard Gaussian are going to be based off of what I'm going to call the fourth order identity tensor. Defining it now is it's going to be given by a symmetrization of an outer product or a tensor product of identity matrices. And there's also a variational definition of it that makes a little bit more sense. The variational definition is this. If we have a vector that's on the unit ball here, okay, and we contract that vector m different times with the identity tensor, we will know we have the identity tensor if we always get one out. Just like with an identity matrix, pick a unit vector and take x transpose I x. That's the same thing as x transpose x, which is 1 if we're a unit vector. The same thing is true for this identity tensor here. Okay? It's the tensor that satisfies this. It doesn't look exactly how you think it would. You might say, I expect it to have a bunch of ones. Yeah, it has a bunch of ones, but it also has some other numbers. This is a representation in 4 dimensions of this tensor, where we're varying 2 of the indices here along this table, and then looking at the slices of the matrix. And for ease of looking at it, this is the 3-dimensional identity tensor for the 4th order tensor. So it's 3 by 3 by 3 by 3. I think I said that 4 times. Now, the thing about the identity tensor is that it can be used to construct the 4th order moment tensor of an arbitrary Gaussian distribution. Say I have any covariance that I want, I can use my whitening transformation, or the inverse of it, to go from my identity tensor, which is the 4th order moment tensor of the standard Gaussian, to the 4th order moment tensor of an arbitrary Gaussian. And it's very simple. It's just through applying my whitening transformation to each index, this identity. So maybe I have a bad definition of very simple. But together, what we can see is that if we have a canonical polyadic decomposition of the identity tensor, which is a thing we know way ahead of time, there's just one of them for any order and any dimension, we can take that identity tensor and its factorization, and coming up with the factorization of the 4th order moment tensor for any Gaussian distribution is going to be given by just applying our inverse whitening transformation to those CP factors, those canonical polyadic factors that we had for the identity tensor. And so it's something that online we can do really simply. Okay, it's just a matrix vector problem for each of the vectors that we have. The hard part is computing canonical polyadic decomposition of the identity tensor, but we only ever have to do it once in our lifetime or the history of the world. And if you store it and spend a lot of time computing it, then publish it on the internet, as we're planning to, you can make use of it for any situation with a Gaussian distribution. With that in hand, we can plug this into evaluating this n to the 6th order algorithm here, okay? And if we do that, we see that we get this nice simplification where we have the same term show up twice, because we've written this 4th order tensor as a sum of products of really simple vectors, okay? Outer products of a vector with itself 4 times. Once we have that, then it becomes a vector times a matrix, a vector times a matrix. That gives us a vector and a vector. That's an order 2 computation. And then we take those 2 vectors and contract them with this 3rd order tensor. And that's going to be an order 3 computation. So overall, we turned an order 6 computation into an order 3 computation with a constant term that depends on the rank of our tensor. In general, these ranks aren't too terribly high. They're usually larger than n, but they're not appreciably larger compared to this. And doing this, we've seen about an order of magnitude speed up in this algorithm. And this generalization, when we look at higher order tensors, higher order moments, and higher order approximations, that order of magnitude becomes 2 orders of magnitude, 3 orders of magnitude, 4 on up as you get higher and higher. So that brings us about to time. I hope that you gain a little bit of an appreciation of the way you can use tensors to quantify nonlinearity and non-Gaussianity, and how you can use them as tools for higher order approximations when those linearizations aren't enough for your problem. I know that my applications were mostly in the space domain, but I really think for online validation or systems engineering ahead of time validation of using linearized algorithms, that this can be a really good methodology, and that it supports further these higher order methods for covariance propagation, for Gaussian mixture splitting and validation. And I think it's a really promising, fun area. I know Dr. Auguri's student, Dan, here is using some of this methodology in covariance steering and those applications. So I think it's a promising area. I'd be happy to answer you any questions that you might have now.
It's here.
Thank you for the great talk. My question is perhaps basic. So the linearization work that you did, what exactly was being linearized? Was it the dynamics around the point? Was it the flow around the trajectory? What was being?
Yeah, B dynamics or B guidance. Oh yeah. So in the case of the dynamics problem, that was just the partial derivative matrix of the final position with respect to the initial velocity there. So the 2nd order partial derivative tensor of those.
So it does not correspond to like the dynamics model being linearized or something.
Yeah, it does, because the dynamics, it's not the vector field being linearized, it's the flow being linearized.
It's around the trajectory, no?
Around a trajectory. So flow linearized around a trajectory with some set time of flight.
And if I may, second question was that a lot of development that you did was in 2 norm.
Yes.
Especially with problem that you considered infinity norm might be of interest.
Yes.
Anything change?
Yeah. So I have a paper that just came out from JGCD that has a bunch of, so some of these don't have analytical calculations that I could come up with or good numerical methods to find them. But I found a number of combinations where you have infinity, 1 or 2 norm in various places here. And some of them make it simpler. For example, the infinity 2 norm is very simple to compute because it's just computing, if you look at each of the outputs individually, each one consists of a matrix then, because you're slicing your tensor up, and then you just have to figure out what's your 2 norm of each of those matrices, and you take the biggest of those. And that was actually the first one I ever looked at before I read Erica Jensen's paper about the tensor eigenvalues. And there's lots of other ones out there. So I have a whole paper that's got an appendix of a ton of these. Yeah.
You consider some kind of sampling-based methods.
Yeah, so we compare, and I saved for time some comparisons against sampling-based methods for this. So in those problems, here is where I used a sampling-based method with like maybe 100,000 trajectories. And we can look at sort of the error that we get between these methods. And we can see that we always can get a higher number than those sampling-based methods because we're doing an optimization. And a lot of times we get it up faster at that point. Yeah.
When you're using those higher order tensors as indicators of nonlinearity, there seems to be an implicit assumption that the Taylor series is convergent. Is that provable? And if not, when's that a reasonable assumption?
Yeah, good question. So under pretty mild assumptions, the flow of a dynamical system with a smooth vector field is going to be smooth itself because it's sort of an integration that's happening. And so it's going to be nicer than the original vector field typically, because integration is a nice smoothing operation. So in general, yes, we have convergent Taylor series. Now, the question of whether or not these are a good measure of nonlinearity, it is really only in a local setting. You know, those terms are dominating for small perturbations from the reference. But at a certain point, as you get very large, your next order term might not be the biggest, it might be the next one, or, you know, the Taylor series isn't really describing it very well at low order. And so really the thing is, it is a canary in the coal mine, though. It's never going to be smaller really than the errors that you actually have present. Maybe in some, you know, for some small specific cases, but on the whole, you're never going to have that conspire really.
Okay, let's thank our speaker one last time.